Chapter 6. Fields, Multipoles, Dielectrics, and Magnetostatics. In Chapters 4 through 7, classic electromagnetism (EM) is covered, with extensive coverage on the Lorentz transform. EM is Lorentz invariant in Chapter 8, which then leads to special relativity and general relativity and other topics in later chapters. This chapter, Chapter 6, generalizes the formalism to macroscopic matter, starting with multipole expansions. Once we have macroscopic matter, we can also describe magnetostatics. Note on examples and exercises. The chapters on electromagnetism draw foremost from the excellent source Classical Electrodynamics by J.D. Jackson. That was the required text for many years at Caltech. Many of the Jackson problems develop the physics theory further, e.g., Gauss's theorem, or further develop the mathematical techniques, for ODEs, definition of delta function as limit, etc. With my own notes from the courses at Caltech, and upon later preliminary exam review at the Universal Wisconsin, the addition of the completed problems from various sources were acquired in a way that seemed to provide a mapping of understanding. I wanted to convey that understanding here. Solutions to these key problems are carefully worked out in what follows, along with notes on the theory from Jackson as well as from. Basic exercises are given to rederive or verify the theory.
The solutions to the exercises here, for the most part, are available via the aforementioned Jackson text, with the detailed derivations provided there. Many examples and related problems are done in order to cover material from basic undergraduate problems to advanced engineering, for antenna design, say, so the notes and problems also draw from undergraduate and graduate EM class notes/exams, and the other texts mentioned. The remarkable success and modern applications of EM will be made evident, but at the end of Chapter 7, when we carefully analyze the hydrogen atom, we will find that there is radiative collapse in the classical theory. This fundamental flaw in the theory, when dealing with even the simplest bound atomic system, will be corrected with the development of the quantum theory in Book 4. 6.1 Macroscopic Matter, Multipoles and Dielectric Materials. Continuing to use notes/conventions of Jackson. Linear superposition and non-vacuum conditions.
As we add sources and their fields, up to and including macroscopic aggregates of matter, we must consider the limits of linear superposition that permit such simple additivity. The classical theory is linear, thus linear superposition, so we are asking for a peek ahead into the quantum electrodynamic theory to see when there is a nonlinear effect. Such nonlinear effect can arise from quantum theory because a photon can scatter off another photon, Delbruck scattering, where two photons transform to an electron-positron pair and then back to two photons. Thus, even the electrodynamic vacuum condition will have some nonlinearity. Here is the expression for this nonlinear feature due to quantum electrodynamics, ca. 1935, that is valid for slowly varying fields, where we also see our first example of electric and magnetic permeability tensors, here precisely theoretically known for the quantum vacuum. Equation 6-1. Equation 6-2. Equation 6-3. Equation 6-4.
Equation 6-5. From which it can be seen that the nonlinear effect is incredibly small for anything at the scale we will be considering. For this effect to be relevant, we would probably be considering something at atomic scale, and it would likely not be slowly varying. So, for what follows, it will be safe to assume the strong validity of linear superposition. Let's now consider fields due to macroscopic aggregates of matter. What is relevant from Maxwell's equations now is the average of fields for the relevant average of their sources. This can expressed in terms of new macroscopic fields, d vector, h vector, that result from elementary sources in a background medium that is not vacuum, and has electric and magnetic permeability tensors relating macroscopic fields to vacuum fields. Equation 6-6. Equation 6-7. Equation 6-8.
Equation 6-9, typically with Equation 6-10. Equation 6-11. For materials other than ferroelectrics or ferromagnets, and for weak enough fields. Note that the constitutive relations D equals D of open bracket E B close bracket and H equals H of open bracket E B close bracket are necessary to move from a solution of the homogeneous equations to the inhomogeneous equations. As noted in Jackson's text, to be generally correct, the constitutive relations should be understood as holding for the Fourier transform ft in space and time on the field quantities, because the linear connection, although linear, can be non-local. Equation 6-12, where epsilon sub alpha beta of x prime t prime can be localized around x prime equals 0 and t prime equals 0, but is non-vanishing for some neighborhood around the origin. Using the relation that ft on convolution gives product on ft's, we get the relation on ft's d sub alpha of k, omega, e sub beta of k, omega, and epsilon sub alpha beta of k omega, using the standard ft definition.
Equation 6-13. To get equation 6-14. So, we are back to a strong form of linearity even in the context of macroscopic media. This will hold in almost every situation considered. The dielectric constants, epsilon sub alpha beta of k, omega, will generally have a significant frequency dependence, however, according to the atomic structure underlying macroscopic media. Consider sufficiently low frequencies that all charges, regardless of inertia, are responsive to applied fields, less than 100 kh of z. For solids we generally see a diagonal dielectric tensor epsilon equals epsilon sub alpha beta almost equals 2-20. For distilled water, which consists of molecular dipoles, we have epsilon equals 88 at 0 degrees Celsius and epsilon equals 56 at 100 degrees Celsius. At optical frequencies, on the other hand, for 100-790 th of z, only the electrons are responsive, and for solids we generally see dielectric coefficient epsilon almost equals 1.7-10, and water has epsilon almost equals 1.77-1.80 over the visible range. Almost independent of temperature between 0 degrees Celsius and 100 degrees Celsius.
In quantum physics, Book 4, we find that the elementary particles have an internal angular momentum or spin that is non-zero. We will obtain precise mathematical expressions for how spin factors into the interactions and scattering in Book 4. The theoretical origins of spin won't be explained until Book 5, however, and for spin statistics not until Book 5 Part 2. At the classical field level in Books 2 and 3, however, we need only be concerned with macroscopic material responses to the applied magnetic fields, as with the electric fields, with the breakdown of materials into the categories diamagnetic, paramagnetic, and ferromagnetic. Atoms and molecules, and the substances they comprise, are diamagnetic if they have an internal angular momentum that is zero. For these substances, the response to applied field follows from Lenz's law, e.g. a bulk magnetization opposing the applied field. Mu alpha alpha 1 backslash mu backslash alpha 1, and with the strongest diamagnetic effect for bismuth, which has mu alpha alpha equals 1 plus 1.8 by 10 minus 4 backslash mu backslash alpha equals 1 plus 1.8 backslash times 10 caret 4. If, on the other hand, the atom or molecular basis consists of elements with a net angular momentum, chemically they have unpaired electrons, then they are paramagnetic.
Now the alignment will favor the applied field, which then leads to mu alpha alpha 1 backslash mu backslash alpha 1, with the smallest value of mu alpha alpha is almost equal to 0.99 backslash mu backslash alpha approximate 0.99. Clearly, mu alpha alpha is almost equal to 1 backslash mu backslash alpha approximate 1 throughout, so the diamagnetic coefficient will generally be assumed to be 1 and not discussed further until Chapter 7. Note that paramagnetic atoms also have the property that they don't strongly interact among themselves, so they each react to the external field in an isolated way favoring alignment. Once there is significant interactions between the non-zero spin elements, we get into the domain of ferromagnetic substances, including statistical mechanical effects like spontaneous magnetization. So, further discussion on these effects is not given until Chapter 7. Charge distribution seen as multipole expansions. From the expansions studied previously, let's now consider, specifically, systems with more than one charge, e.g. charge distributions, We then have multipole expansions. We have encountered point charge and dipole moment at lowest order thus far. Let's consider the multipole in spherical coordinates, to retain a point-particle perspective, with internal multipole implied, an issue that comes back in Chapter 4 when discussing particle spin. We, therefore, want to examine
multipole expansion. Equation 6-15. Interested in potential outside distribution, so our sub is less than equals our prime, our sub is greater than equals r, thus, equation 6-16, where q sub Lm are the multipole moments and q sub L, script minus m equals -1, to the mth power times q sub Lm raised to the asterisk power. If we expand normal phi of x in rectangular coordinates, this becomes equation 6-17. Which follows from direct Taylor series expansion of the fraction with numerator 1 and denominator the absolute value of x minus x prime. The E field is thus equation 6-18.
The values of q sub Lm for the lowest non-vanishing multipole moment of any charge distribution are independent of the choice or origin of the coordinates, but all higher multipole moments do in general depend on the location of the origin. In terms of a rectangular coordinate expansion, we have the following. Equation 6-19.